So Lagrange's interpolation. So in this Lagrange's interpolation, right? So we learned actually about Newton's forward interpolation and backward interpolation, but there actually the condition is the intervals has to be unique. That means same interval has to be maintained across entire data points. But in case if we get a data point which is not in equal intervals, then actually we will go for this Lagrange's interpolation formula. So what this Lagrange's interpolation formula talks about is, see this, suppose if you have a function, let us say f of x. Now, for this particular function, let us say we have the data points x0, y0 and x1, y1 dash 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 up to xn, yn. Suppose if these are the data points that are available, may not be equally spaced, then actually by converting all these data points into a single equation, let us say there is a polynomial we can construct out of all these data points, and the order of the polynomial has to be of the order of x power n. So this is the order of the polynomial provided if you have n plus 1 data points. And this one we can construct this way, that is f of x is equal to some constant a0 getting multiplied by the difference of this x minus x0, x minus x1, this is x minus x1, and x minus x2, and x minus x3, dash dash dash, x minus xn. a1 plus a1 getting multiplied by x minus x1, x0, x minus x2, x minus x3 dash 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 x minus xn plus a2 x minus x0 x minus x1 x minus x3 dash 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 x minus xn plus dash dash dash. So till the last term, so that is the last one is an getting multiplied by x minus x0, x minus x1 dash 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 up to x minus xn minus 1. So if you notice in the entire polynomial, what is happening here it is, if you are talking about a0, then actually x0 is getting missed out here. If you are finding out for a1, then actually x1 is getting missed out here. For a2, x2 got missed out, and for an, xn got missed out. So this is how actually you can construct a polynomial out of the data points. Got it? So why? Because if you wanted to find out, if you want to keep the value of x minus x0 also here and x minus x1 also here, then actually for finding out these unknown values of a0, a1, a2 dash 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 an, so there won't be any standard method to find out those values. If you keep the missing values also like x minus x0 and x minus x1 and x minus x2 like this. Got it? So these are the unknown values which we have to be finding out for an equivalent polynomial construct connecting all these data points. Got it? So these ones actually we can find out. Let us say if you take this f of x0, out of these points f of x0 value you can put here a0, and then x0 minus x1, x0 minus x2, x0 minus x3, dash dash dash, x0 minus xn. Now here actually a0 is left over, and for rest of the things actually if you keep x is equal to x0, this will become 0, and this will become 0, and this will become 0. So all the values are getting 0 if you keep x is equal to x0, and you left with only a0 for f of x0, which we call this as the y0 value. So from this actually you can calculate a0 value as y0 divided by x0 minus x1 into x0 minus x2 into x0 minus x3 into dash 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 x0 minus xn. So this is how actually you can calculate the unknown value of a naught from this polynomial. So this is a imaginary polynomial what we have imagined now, and this polynomial actually, by calculating these unknown quotient values, we will be able to construct a known polynomial. So these unknown values you can get it from these data points, from this particular line. Got it? So this way you can calculate a1 by substituting the second data point x1 and y1. So if you keep x1 and y1, so this one will become y1, and this part x1 minus x1 is 0. Then here actually there is nothing like x minus x naught. So even if you keep x1 here, x1 minus x naught and x1 minus x2 and x1 minus x3 like this, all these things will remain. And here anyway, so x1 minus x naught will be there, and x1 minus x1 will become 0. So all these a's actually will become 0, and we left with only one unknown. This is a1, which you can calculate by substituting x is equal to x1 and y is equal to y0, y1. Got it? So like this actually you can calculate all the unknown values of a0, a1, a2, a3, an, and then you can substitute back to the original equation to get the unknown polynomial f of x, which we call as the Lagrange's interpolation formula. Got it? Any questions on this? So first you note down, and then I'll write a1, a2, a3 also, and then we can construct the unknown polynomial. Done? So similarly, if you want to calculate a1, then actually this is going to be y1 divided by x1 minus x0, x1 minus x2, x1 minus x3, dash 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 up to x1 minus xn. Similarly, a2 is equal to y2 divided by x2 minus x0, x2 minus x1, x2 minus x3, dash 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 x2 minus xn. So this is how you can construct it. Okay. So like this actually, once you got the values of a0, a1 and a2 dash dash dash, then f of x actually you can express from the fundamental equation, that is f of x is equal to a0 is nothing but y0 divided by, so I will keep y0 here, and then here x0 minus x1, x0 minus x2, x0 minus x3, dash 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 x0 minus xn. So this is y0, and then the numerator actually, initially when we try to imagine the polynomial value actually we have imagined as, this is x minus x1, x minus x2, dash dash dash, or x minus x3, dash 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 x minus xn. This is the first term, and the second term, so x minus x1 it started and it left with x minus x0. So next one it has to start with x minus x0, x minus x2, x minus x3, dash 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 x minus xn. Here y1 whole divided by x1 minus x0, x1 minus x2, x1 minus x3, dash 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 x1 minus xn, plus x minus x2, x minus x0, x minus x1, x minus x3, x minus, so dash 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 x minus xn divided by x2 minus x0, x2 minus x1, x2 minus x3 dash 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 x2 minus xn into y2 plus dash dash dash. So this is how actually the Lagrange's polynomial will continue. Got it? Here actually if you notice, for the first data point in the denominator, x0 will be there first, and then x1, x2, x3, x4 like that till xn. In the numerator, this is a variable for which you wanted to find out the value. This is this x. So x minus x1 minus x2 minus x3 minus xn like this, and leaving x0 ahead. And here in that second term, and this multiplied with y0. The second term, x minus x0, x minus x2. So here actually there is a missing term of x minus x1. So this you have to remember. So x minus x1 won't be there here. X minus x0, x minus x2, x minus x3, dash dash dash, x minus xn. In the denominator, whatever is left here, that is x1. So it starts with x1. x1 minus x0, x1 minus x2, and x1 minus x3 like this. And here if you notice, x1 minus x1 won't be there, because I think that will become 0. So x1 minus x1, x1 minus x1 won't be there, and rest of the terms will be present there. Like this actually, the entire polynomial will continue up to the last data point of xn and yn. Got it? So this is a little bigger formula, but understanding is easy. Got it? Any questions on this? So this is applicable for unequal intervals. Then noted. So with this Lagrange's interpolation, we will solve 2-3 problems, and then actually we will go with numerical integration. So the data points are x and y here. For this, 5 and 150. The second one, 7 and 392. 11 and 1492. 13 and 2366. 17 and 5202. So this is the set of data points actually he has given. For this actually what you are asked for is evaluate the value of f of 9. Find f of 9 value with Lagrange's interpolation. So with the Lagrange's interpolation formula, we need to be finding out the unknown data point for f of 9. So here actually the Lagrange's interpolation says that f of x can be expressed as x minus x1, x minus x2, dash dash dash, x minus xn divided by x0 minus x1, x0 minus x2, dash dash dash, x0 minus xn getting multiplied by y0 plus x minus x0, x minus x2, dash dash dash, x minus xn divided by x1 minus x0, x1 minus x2, dash dash dash, x1 minus xn multiplied by y1. So like this actually you can express it. Now for this data points, if you substitute here, f of 9 can be expressed as, instead of x actually it is 9. So 9 minus x1 is 7. 9 minus 7 into 9 minus 11 into 9 minus 13 into 9 minus 17 divided by x0 is 5. So x0 minus x1, 5 minus 7, 5 minus 11, 5 minus 13, 5 minus 17 multiplied by y0, 150. plus, so next one is x minus x naught. So x minus x is again, this is 9. So 9 minus x naught is 5. 9 minus 11. 9 minus 13. 9 minus 17. Divided by x1 minus. So x1 is 7. 7 minus 5 into 7 minus 11 into 7 minus 13 into 7 minus 17. Getting multiplied, second data point 392 plus in the next one 9 minus 5, 9 minus 7, 9 minus 13 won't, 11 won't be there, and 13, 9 minus 17. In the denominator, so x3 is 11, 11 minus 5, 11 minus 9, 11 minus 13, 11 minus 17. Getting multiplied by 1492. So I think from this actually I think you can continue. So continue putting the values for this 13 and 17 also, and then try to calculate with the help of calculator and tell me the answer for me. I hope you understood how I have written this. So in the numerator actually this is always starts with 9 numerator and leaving 1 point and rest of the values will be there. And in the denominator actually whatever is left, that is 5 is left in this case, that 5 minus rest of the values. And here also 9 minus all the values except for the second one 7. So in the denominator 7 minus rest of all the values. Then at the end actually you have to multiply corresponding the y value. Can you calculate and tell me the answer? So you can verify that. I think so the answer is 810 for the corresponding value of 9. This is the answer. You can cross check it. Got it? So we'll solve the next problem exactly in the similar lines. Find the polynomial f of x find the polynomial f of x by using Lagrange's formula and hence find f of 3. Now the data points are x and y 0 to 1 3, 2 12, 5 147. So these are the data points now. So for these data points we need to be finding out a polynomial. Now can somebody tell me what is the order of the polynomial should be? What should be the order of the polynomial? Anybody? So it should be 3. Why? Because here actually we have 4 different data points. If there are 4 different data points, the order of the polynomial can only be 3. That is n minus 1. So n minus 1 x power is the order. Right? I have given the reason why actually we are getting only n minus 1, because actually we have to leave one data point so that you will be able to calculate all the unknown values of a0, a1, a2 dash dash dash. that's the reason actually why we will get only n minus 1 as the order of the polynomial. Now the polynomial is f of x is equal to, so this is a naught into x minus x1, x minus x2, dash dash dash, x minus xn, plus a1, x minus x2, sorry, x minus x naught, x minus x2, dash dash dash, x minus xn, plus a2 into x minus x naught, x minus x1, x minus x3, dash dash dash, x minus xn. So like this actually this polynomial will continue. So this is how you can put the polynomial, and the unknown values of a0, a1, a2 you can find out by substituting these values. Now actually f of 0, if you take it, f of 0 from the table it is 2, and the right side value a0 getting multiplied by 2 minus, so this is actually f of 0, 0 minus x1, so 0 minus 1, 0 minus 1, 0 minus 2, 0 minus 3, sorry, 0 minus 5, plus, so here actually a1 into 0 minus 0, so 0 minus 0 is anyway 0, you can leave it as it is, and then whatever you have got here it is a0 getting multiplied by, so 0 minus 1 is minus 1, this is minus 2, and this is minus 5, so this is plus 10 into minus 1, this is minus 10, so minus 10 into a0 is equal to 2, then actually from this a0 is equal to minus 1 by 5, so this is how you can find out the value of a0. The similar lines, if you want to calculate the second value, that is a1, if you want to calculate it, then actually this is going to be f of 1. So f of 1 value is 3. So 3 can be expressed as, first term will become 0 because actually 1 minus 1 is equal to 0. So 1 minus 1 actually being 0, a0 will cancel out. Similarly, for a2 also, here 1 minus 1 will be there. And again this is going to be vanished out. And whatever left over is only this part, that is the a1 part. So for a1, this is going to be a1 getting multiplied by 1 minus 0, 1 minus x2 is 2, 1 minus 5. So this is going to be a1 getting multiplied by, so this is 1, and this is minus 1, and this is minus 4. Minus 1 into minus 4 is going to be plus 4. So this value is 3, then a1 is equal to 3 by 4. So a1 is equal to 3 by 4 we have got. Similarly, a2 you can find out f of 2. So f of 2 is equal to 12, and this side a3 getting multiplied by, so for 2 it is going to be 2 minus 0, 2 minus 1, 2 minus 5. So this is going to be 2 minus 0 is 2, and this is 2 minus 1 is 1, and 2 into 1 is 2, and 2 minus 5 is minus 3. Minus 3 into 2 is minus 6. So a2 getting multiplied by minus 6, and the right side value is plus 12, then it implies a2 equal to minus 2, plus 12 by minus 6. So it is going to be minus 2. Similarly, next value, so this is 147 is equal to f of 5, and this value is equal to a4. So a4 is equal to, sorry, so this is a2, this is a3. Yeah. So a3 is equal to 5 minus 0, 5 minus 1, 5 minus 2. So this is going to 5 minus 0 is 5, and 5 minus 1 is 4, and 5 minus 2 is 3. So 5 into 4 into 3, 60 into a3. It implies a3 equal to 147 divided by 60. So these are the values of A0, A1, A2 and A3 values. Now actually you can calculate this polynomial by substituting these values here. First you note down this. I am going to calculate the polynomial. So the polynomial is f of x is equal to, so A0 is minus 1 by 5 getting multiplied by x minus x1. So x minus x1 is 1, x minus 1 into x minus 2 into x minus 5. Then the next coefficient is A1 is plus 3 by 4 getting multiplied by x minus 0 into x minus 2 into x minus 5 plus minus 2 getting multiplied by x minus 0 into x minus 1 into x minus 5. And then the next one is plus 147 by 60 getting multiplied by x minus 1, x minus 2. So this is the polynomial. Got it? So we have got the polynomial. Now this polynomial actually you can calculate for any value. So he asked to find out f of 3. Now f of 3 you can substitute in this and then find out the value of it. Got it? I think so. This value is 35. Yeah, somebody already calculated 35. The answer. Got it? So this is how actually for unequal intervals actually we can calculate a polynomial. From there actually you can find out for any unknown value. So this is basically a curve fitting from the given data as a polynomial. Got it? Yeah. So this is how you can do interpolation. So we discussed all the aspects of interpolation, that is Newton's forward, backward and Lagrange's interpolation. Now let us move to numerical integration. So do you have any questions on this? On interpolation? Any questions on interpolation? So in the numerical integration, right? So what we are trying to find in case of numerical integration is any integration or any two-dimensional integration will always give say area. Now here when we are talking about the numerical integration, be sure that we are talking about only the definite integrals. We are not touching indefinite integrals at all, because these are actually data driven aspects. So data driven aspects meaning we are already giving a numerical data, start point and end point. Got it? So equal intervals can also be done with the help of Lagrange's method also, but actually this is much more advanced than the equal intervals. Hence actually in special cases where we don't have the equal intervals, we can make use of it. Even for equal intervals also you can make use of it. Got it? Okay. So we are talking about the numerical integration. So what we are talking about is finding out the area. So as a simple example, the integration or any two-dimensional integration like integral f of x dx will always gives the area. So this area under the curve given by this f of x. So the way it is going to given is, let us say this is a random curve f of x and this is the curve, and this curve actually from this limit from here to here actually if you give a data point, this is a and this is b, and then this integration value whatever we are talking about is nothing but there are two different points here, f of x and dx, which essentially means that this dx value is nothing but we are dividing this into small strips like this, and this strip width is dx. And then the height of this function is nothing but this y value. So this y value getting multiplied by dx is going to give this strip width. And then in the next moment, you will calculate one more strip and the height is a little increased now. And then again dx is the width. So this entire thing is divided into parts of dx. So like this actually small dx aspects actually is going to be there. So like this small strips actually we are calculating the area as if like it is a rectangle. So this rectangle, if you notice, so on an enlarged view, so this is how the curve is there. And in this curve, if you notice, you are taking off this particular value. So this is the height we are talking about. This is x naught and this is y naught. So y naught is nothing but f of x naught. So the width here it is dx. So when we are talking about f of x into dx, what we are talking about here it is, this is the area we are talking about. And this area dx, if you notice, this is ignored. And then exactly in the similar manner, if I draw one more rectangle here, so if you start counting from the starting point here and then in this particular strip, so this is the rectangular area what we are calculating. This is the enlarged part of it. Now if you notice this area of this triangle, if you notice, this is extra counted. So this part ideally we should count it, but we have ignored it, and this part actually we shouldn't count it, but we have counted it. So obviously when we are talking about this integration, right, so there will be definite error in it, and this error can be minimized by reducing the size of this strip. And this strip actually, suppose if I draw two different strips of almost overlapping on top of the same, then actually this error is almost zero. So if this error is almost zero, whatever the integration value we calculate, this is 100% accurate. Or actually, to be specific, if I say 99.999% accurate, not 100% always, because the strip width has to be there definitely, and that may be 0.001 or 0.0000, after 5 zeros may be 1, after 10 zeros may be 1. So depending upon that, that's why actually when we are talking about the integration or the differentiation, limit delta x tending to 0 but not 0. So when we are talking about tending to 0, that is a closed approximated value of 0. So that's why when we are talking about this area, you have made into small parts of infinite parts, and all the infinite part areas we are adding up together to come to this integral. Now exactly in the similar manner, in case if you wanted to calculate the area, so this is how you can integrate it, but the same integration can also be done by dividing into these small strips and then adding up together numerically. So if you have got the data points, this is x naught and y naught. So this data point is x naught comma y naught, and the very next point is x1 comma y1, and very next point is x2 comma y2. Like this actually, if you have got xn comma yn as the last data point, then based on this data point availability, you will be constructing this area. But if you notice, there will be a definitely associated error in it, because these data points are actually not almost closer to 0. There will be definitely certain interval, and that interval actually, so here actually suppose if the curve is moving upward like this, there will be ignored area. If the curve is moving down, there will be extra counted area. So this is an error. So this error is definitely present in case of numerical integration. But if you do analytically, then actually you might get 99.99%, 100% accurate. So but here actually there will be, we need to bear with the error there. But how much error you wanted to tolerate, that will be a question. So this error actually, depending upon this data points actually how you wanted to approximate it, there are different methods actually we are bringing up. So in that actually, the first method is trapezoidal rule. So in the trapezoidal rule, right, so a bigger error is going to be there. In case if you wanted to approximate this as a trapezoidal rule. Trapezoidal rule, by definition, what it says is, if the curve is of this particular format, and then this is one data point and this is another data point, ideally we should be counting this area. Let us say this is how the curve is, and then ideally we should be counting this 100% area covered by this curve between these intervals. But you are trying to approximate this as a trapezoid like this. So in the trapezoid, right? So there will be two different parallel lines, and there will be two different other lines may not be parallel. So these two parallel lines and getting multiplied by this height. So the area of this trapezoid is going to be, we can calculate manually also, as we know the formula. So half h into y naught plus y1. So this is y naught and this is y1. So half h into a plus b is the area for any trapezoid, right? So half h into a plus b, h is this height. So this height actually, by definition, this small h actually is the interval we are talking about. This interval height is h, and this length of these two sides is y0 plus y1, and half h into a plus b is the area of any trapezoid. So you are trying to approximate this as a trapezoid. Then here actually this is the ignored area. So this ignored area, that means we are not counting this top area. Ideally we should be counting it. That means there is definitely certain error in it. And the next one is Simpson's 1/3 rule. In Simpson's 1/3 rule, what we try to do is, rather than approximating as a trapezoid, we will try to approximate as a parabola. So that means if I keep one more data point here, then if I try to approximate curve like this, then actually the accuracy is going to be increased, but still there will be an associated error, because this is not tending to 0, or actually h is almost 0, then actually you have got all the data points very closer, then the error is going to be reduced there. But here actually, being h value, certain definite value is going to be there, maybe 0.1 or maybe 0.1, maybe 0.5, definitely there will be an error. So, but the error is going to be reduced in case if you wanted to approximate as a parabola than the trapezoid. So in the first case actually you are trying to approximate as a straight line, this one. In the second case you are trying to approximate this as a quadratic equation or a parabola. In the third case, that is the third one, Simpson's 3/8 rule. In case of Simpson's 3/8 rule, so here actually approximate as a third order polynomial. So we are trying to approximate this as a third order polynomial, which will closely trace this particular curve, because actually you are trying to approximate as a polynomial. And then, as Maclaurin series talks about, any random curve can be approximated as a polynomial of infinite order. So that is a general theorem. So given any curve, so you can approximate as a polynomial of order infinite. Now the accuracy of the polynomial is going to be there only if you increase the order of the polynomial. But if you take as a straight line, that is actually you are trying to approximate as a first order polynomial itself. And if you want to take as a second order polynomial, the accuracy of the curve is going to be increased, or actually you are trying to closely trace this particular curve with the polynomial. So this may be a sine wave, or this may be any other curve, random curve, maybe a e power x curve, but still you are trying to approximate as a polynomial with the help of Maclaurin series. So by definition, in a standard way, we can state that any curve can be approximated as a polynomial with the help of Maclaurin series, but the accuracy of the curve is going to be increased if you wanted to increase the order of the polynomial. Hence, in case of here actually, this is a first order polynomial, this is a second order polynomial, and this is a third order polynomial. But actually, you can still continue, maybe fourth order polynomial or the fifth order polynomial also you can continue, but that is of no use. But this is very popularly used formula for calculating a numerical integration. So all these methods what we are talking about is not to calculate the error. This is to find out the value of the integration. That is nothing but the area under this particular curve. But the area, whatever we are going to get, is accurate if we increase the order of the polynomial. So in the first case, where we are approximating as a trapezoid, the error value is more. And if in the second case, if you use Simpson's one-third rule, we are trying to approximate this part of the curve as a second order polynomial or a parabola. Hence, the accuracy of the area calculated is going to be increased, or indirectly the error is getting reduced. And in the third case, that is 3/8 rule of Simpson's, there we are trying to approximate as a third order polynomial. Hence, actually, even more better way, actually, we are trying to trace this particular curve. Hence, actually, the area calculated is of more accurate than the Simpson's one-third rule, and indirectly the error is getting reduced further. So like this, actually, there are other rules also, Boole's rule or Wedel's rules, like that. There are other rules also, but of the order of 4th, 5th, like that. But practically, for all calculations, we will be depending currently on this Simpson's one-third rule, which will give you a trade-off between the calculation versus the error. Got it? So we are trying to approximate certain error there, and then if you tolerate certain amount of error, then you can still stick to this Simpson's one-third rule, which is practically allowed for all the engineering calculations. Got it? Understood? Now actually, what are all these formulas? Now actually, all the formulas together, actually, we will bring from a single formula. So I will derive all those formulas now. First you note down this, then we are going to derive all the formulae. So we wanted to find out integral f of x dx value within the interval of a to b. Now this can be graphically represented as, let us say this is the curve y is equal to f of x, for which actually I wanted to find out the area between the points a and b. Now here, if I wanted to find out the area between a and b, and if I have the data points already, then actually I will directly take these data points of this curve, or else actually I will divide this curve into the number of equal intervals like this. So these are the data points. Now here actually, this we start with x0, and this is 1h, and this is h, this is h, and this is h, and this is h. So I have divided into equal intervals like this. Now this value is going to be x0 plus h, and this value is going to be x0 plus 2h, and this value is going to be x0 plus 3h, and this value is x0 plus 4h, and this value is x0 plus 5h, and the last value is x0. So if you notice, this is first, second, third, fourth, fifth, and sixth intervals. Now this can be written as, b can be written as x0 plus 6 times of h. This is how I can express the b value. Now this integration, I can write this as integral x0 to x0 plus nh, provided if I divide this 6 equal to n. So I have made into 6 different equal intervals. Hence I have n different equal intervals where n is equal to 6 for this particular case. Now given the random curve, you can divide this into any number of equal intervals, and depending upon the accuracy, actually you can divide this. Here this is f of x can be written as x0 plus n times of h into dx. So the same curve, instead of this one, sorry, rh, yeah. So some random value of r into h and dx. So this is the value which we can make use of to calculate, where x is equal to x0 plus some random value of r into h. So this r can be any value. So this r value actually at one instant it will be here, and then it keeps on increases like this. So this is a random in between value r, and where to calculate this integration you can substitute x is equal to x0 plus rh. So dx is equal to h into dr. So dx is equal to h into dr by substitution method, and this one then, so lower interval, right? So here actually r will become 0. Here r becomes n. F of x naught plus rh into h into dr. This is how you can express it. Got it? This is just substitution. Don't get confused. Here actually integral a to b f of x dx, and this x value is any value randomly you can select it here, and that can be expressed as x naught plus rh, where I have introduced a new variable rh for x is equal to x naught plus rh. So for this actually dx is equal to h into dr, and h into dr in place of dx I have substituted there, and x naught plus rh is as if like f of x for us. And then here actually integral 0 to n x naught plus rh into h into dr is the integral value, or we can calculate h into integral 0 to n and then f of x naught plus rh into dr. So this is the integral finally we wanted to calculate. Now here in doing all this exercise, I have made the limits from a to b into the change of 0 to n, where n is the interval. So 0 to n is the interval. So this interval is in terms of r. So r into h into dr is coming into picture here. Now this value is we can calculate with the help of, this is as if like e power r into f of x naught. So this actually Newton's forward interpolation formula. We can make use of it. So if you use Newton's forward interpolation formula, then actually this can be expressed as h times of integral 0 to n, and then f of x naught plus rh actually we have already expressed in terms of p there. Instead of r, it is going to be p there. Now here y naught plus r into delta y naught plus r into r minus 1 divided by 2 factorial into delta square y naught plus r into r minus 1 into r minus 2 divided by 3 factorial into delta cube y naught plus dash 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 up to infinity. So this is as per the Newton's forward interpolation formula, and this needs to be integrated with respect to dr. Got it? So first you note down this, and then I am going to erase it and then try to do this integration. So this formula after integration we are going to get. So integral f of x dx is equal to integral 0 to n, and h is outside, and then y naught into r, or actually in one step I will first simplify it, dr plus r into delta y naught plus r square minus r delta square y naught plus, so r into r, so this is r square minus r cube r cube minus 3r square plus 2r by 6 delta cube y naught and then the next one is r into r minus 1 into r minus 2 into r minus 3. So this value we have already calculated, it is r cube minus 3r square plus 2r getting multiplied by r minus 3. So this is going to be r power 4 minus 3r cube plus 2r square minus 3r cube plus 9r square minus 6r. This is r power 4 minus 6r cube plus 11r square minus 6r. Okay. So this one you can substitute here. R power 4 minus 6r cube plus 11r square minus 6r divided by, this is 2 factorial, this is 3 factorial and this is 4 factorial. So 4 factorial is 24. Delta power 4 y naught plus dash 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 up to infinity. So this value we need to be integrating with respect to dr. So this value is h getting multiplied by y naught into r plus r square by 2 into delta y naught plus, so this is r cube minus r cube by 3 minus r square by 2 into delta square y naught plus 1 by 6 times of r power 4 by 4 minus 3r square by 3 r cube by 3 plus 2r square by 2 delta cube y naught. I will ignore the next term. So, and here this is h times of, here if you substitute the upper limit and lower limit is n and lower limit is 0. So if you substitute the upper limit and lower limit is anyway 0, because actually in place of r is a factor for the entire term. Now being this value lower limit is 0, you can substitute in place of r as n. So this is y naught into n plus n square by 2 times of delta y naught plus half of, so actually you can take LCM of it and then this is going to be 6. R cube minus 3r square divided by 6 delta square y naught one by 6 times of, the LCM is 12. So this is 3n power 4 minus 3 12n cube plus 12n square whole divided by 12. This is delta cube y naught. So this is the formula. So here actually what we have done was, so instead of r actually now we replace in terms of n by substituting the upper limit, being lower limit is 0. So this is what actually we call this as Newton-Cotes formula. So Newton-Cotes quadrature formula, sometimes it is called as, so this is Newton-Cotes quadrature formula, and this Newton-Cotes quadrature formula is the master principle for all the equations of numerical integration. That is, be it may be a trapezoidal rule, be it may be a Simpson's 1/3 rule, be it may be a 3/8 rule or Boole's rule or Wedel's rule, whatever it may be, This is the fundamental principle from where actually we are going to derive for all the equations. Now in this equation, if n equal to 1, we call this as the trapezoidal rule, and if n equal to 2, we call this as Simpson's 1/3 rule. If n equal to 3, we call this as Simpson's 3/8 rule. So this is how actually you can derive all the equations from this single equation of integral f of x dx is equal to h times multiplied by y naught into n plus n square by 2 times of delta y naught plus 1 by 2 times of 2n cube minus 3n square by 6, and then into delta square y naught 1 by 6 times of 3n power 4 minus 12n cube plus 12n square divided to 12 into delta cube y naught. Like this, actually this formula will keep on increase. Actually, if you keep n is equal to 1, we left with only one part here. And then if n equal to 2, then actually we go till del square. And if n equal to 3, we go till del power 3. So like this, actually if n equal to 4, we will go del power 4 like that. So being actually this value, so this is trapezoidal rule. And this, if you consider 1/3 rule of Simpson, and this if you consider 3/8 rule of Simpson. So now actually it is up to us how do you wanted to put the data points in this equation, by taking only this part or taking till this point or taking till this point. Got it? So any questions on this? This is the generalizer formula. In the next class, actually from this generalizer formula I am going to derive the nodal. So I am going to derive all the three different formulas of, that is Simpson's rule, Simpson's 1/3 rule, Simpson's 3/8 rule, and the trapezoidal rule. Any questions on this? Any questions on this? So the simplified form of this equation can be written as, so this actually you have to consider this LCMs and then simplify all the terms, and finally I will give you one formula which you can remember, and for that actually you can derive all the equations from there. So that is integral f of x dx a to b. So this can be approximated as, so this is x naught to x naught plus nh f of x dx, and this value is n times of h getting multiplied by y naught plus of delta y naught plus n into 2n minus 3 by 12, 2n minus 3 divided by 12, delta square y naught plus n into n minus 2 whole square by 24. Delta cube y naught. So till this point you can remember. So this is Newton-Cotes quadrature formula. And from this equation, n equal to 1 implies trapezoidal rule. So approximated as a straight line. Curve is approximated as a straight line. And n equal to 2, Simpson's 1/3 rule. Curve is approximated as parabola or second order polynomial. and n equal to 3, Simpson 3/8 rule. Here, curve is approximated as a third order polynomial. Got it? What is your question, Akhil? I didn't get your question. Okay, so how actually others will become 0 when n equal to 1? So that is, if n is equal to 1, then here actually there is no point in considering higher order dels. Why? Because we have got only two different data points, x0 and x1. So if you got only two different data points, x0 and x1, and then if you want to calculate del y0, so this is y0 and y1. So del y0 is y1 minus y0. Now here, if you want to calculate delta square y0, we need to be calculating as delta y1 minus delta y0. Now, there is nothing like delta y1 here because there are no data points available here. Hence, there is no point in considering the higher order dels here. Got it? So that's why actually when n is equal to 1, we stop here itself. Understood? Yeah. Yeah. So that's all for today. So in the next class actually we'll substitute n values and then try to derive all the three different formulas. Yeah. That's all for today. Thank you. Good night.